Okay, so what have we done so far? We have discussed 3 examples of quantum error correcting codes. So, the one which we discussed in some detail was, is there a question? Somebody's mic is on. Can you please mute yourself? Can people make out whose mic was on? Yeah, I don't see anybody's mic on. All right, let's continue. Yeah, so we've discussed 3 examples of quantum error correcting codes, and we've seen their different properties and how they encode, how they detect and correct for errors, right? So the first is the 3-qubit bit flip code, and this was specific to the bit flip channel. The second was the 3-qubit phase flip code, and this was specific to the phase flip channel. Can one of you tell me whose mic is on? I don't see, can't make out. Everyone seems muted as far as, but there is some noise. Do the others hear this noise?
Yes, ma'am, we can hear the noise, but when I look at the list of participants, it also says everyone else is muted. So
That's spooky. Okay, yeah, I've even hit mute all, but that doesn't seem to work. Okay, let's proceed. All right, so these are the 2 noise-specific codes that we've looked at. So in these 2 cases, the way we identify the code is by writing down a pair of states, which we call the code words, right? So we wrote down a pair of states. So in this case, we wrote down a 0. So these are called the logical states or the code words, and these define the code space for us, right? Similarly, in the case of the phase flip code, the logical states or the code words were these 2 states, right? And thirdly, we discussed a more general code, namely the 9-qubit Shor code. And now you see, I'm not referring to this code using a noise model. I'm not saying bit flip or phase flip or a particular kind of noise. Rather, I'm calling it a generic code. So this is the first example of a general purpose quantum error correcting code, because we saw that it can independently detect and correct both X and Z errors. And then by extension, it can also correct Y errors, because Y is simply the product of X and Z up to an overall phase. So the fact that it can detect and correct X and Z then means that it can also detect and correct a Y, because the important part is that it can independently detect and correct. And this is what we discussed towards the fag end of last Tuesday's lecture, where we saw that the measurements you need to do in order to detect the X and the Z errors are actually commuting measurements. They are compatible measurements because they are pairwise X or pairwise Z, right? And pairwise X and Z in such a way that they commute. So the set of measurements that you need to do to detect the X and Z errors are commuting or compatible measurements, and therefore they can be done independently. So both X and Z can be detected independently and therefore can be corrected. So even if on the same qubit I have an X error and a Z error, that is effectively like having a Y error, right? And so that can also be therefore detected and corrected by viewing it as two separate errors occurring on the same qubit. Okay? How does this help us? How does the fact that you can correct for X, Y, and Z make it a general purpose code? Well, it makes it a general purpose code because any 2 cross 2 matrix, so any 2 cross 2 matrix can be one of the Krauss operators of a quantum channel on a qubit, right? Because the Krauss operators of a qubit channel are all matrices on the qubit space, and they are just 2 cross 2 matrices. And any 2 cross 2 matrix can be written as some C0 identity plus C1x plus C2y plus C3z, right? So it can be written as a linear combination of the Pauli operators, right? And if you can correct and detect for the Paulis, since these transformations are all linear, whether it is the Krauss operator sum representation, right, or it is the measurement or the unitary, well, not the measurement is a collapse finally, but the way you do it is with the ancilla, right? You're not doing it on the code words, you're doing only unitary operations on the code words. So all of these operations being linear, any error, so this is an arbitrary error, right, can be broken down into a linear combination of the Paulis. And so if you can detect and correct for the Pauli operators, which are the X, Y, and Z errors, then intuitively it should be that you can detect and correct for arbitrary single qubit errors. So the Shor code is something that can correct for arbitrary single qubit errors. Because remember, this can only distinguish perfectly so that is because of this, okay? So this can only distinguish perfectly the single qubit X and Z errors. It cannot perfectly distinguish 2 qubit X or 2 qubit Z because then there is an overlap between the errored states, right? We saw this last time. So it can only independently detect and correct X and Z, but single qubit, right? So this is also part of your assignment where I've asked you to look at the Shor code a bit more carefully. So let me write down the code words of the Shor code just for completion. So this is of the form 000 plus 111 by root 2 tensor 3, and the 1 is replaced by 000 minus 111 by root 2, right? So what I want to do today is to generalize this, the scope of this, and ask if I have a general code, right? So what is a code? A code is simply a subspace of a larger space, right? In this case, it is this two-dimensional subspace of the 3-qubit space, this two-dimensional subspace of a 3-qubit space. Here it's a two-dimensional subspace of a 9-qubit space. So given a code space, is there a way to check whether it has any error correcting properties? Conversely, given a noise channel, is there a way to pick a code space, or is there a way to identify code spaces which are going to be able to correct or detect and correct errors for this noise? So there has to be a certain method to code construction, right? And this method comes from understanding what are called these algebraic conditions for quantum error correction. So that's what I want to state, and hopefully I'll prove the theorem also today. So these conditions were due to Knill and Laflamme. This is a paper, I think, in 96, if I'm not mistaken, but you can go check. Nielsen Chuang has the references. But before I write down these algebraic conditions, I want to list what characterizes a QEC protocol. So a QEC protocol or an error correction procedure is characterized by, well, first the noise channel, right? So I will call this N, and this is some CPTP map, right? Second, if it's an error correcting protocol, there has to be a code, and the code is characterized by a code space C, which is a subspace of some larger Hilbert space, right? And this code space itself is characterized or defined by a projector. It's defined by the projector onto the code space. So we already looked at this while discussing the 3-qubit bit flip code. What is this projector? So I'm going to just call this P, right? P is nothing but this operator constructed using the logical states, right? So the 0 and the 1 take the place of the 0 and the 1 of your single qubit space, right? The logical 0 and the logical 1 states are now the corresponding 0 and 1. And the span of this is what is the code space, right? So any state which can be written as a linear combination of the 0L and 1L is what constitutes the code space. So there is a projection operator that characterizes this code space, and we've seen this before. So you assume that this is the larger Hilbert space. The code space is sitting somewhere here. So if I have any state here, psi, which is outside the code space, if I act the projector on psi, what happens? I get the 0, 0 acting on psi, and then I get the 1, 1 acting on psi, right? So I get 0L with a number which is simply the projection of psi, the overlap of psi with respect to the 0 state inside the code space. Similarly, I get 1L, which is weighted by the overlap of psi with respect to the orthogonal state in the code space. There are only a pair of orthogonal states. I mean, there are several pairs. We pick one such pair, and that's what we call the code word, the logical states or the code words. And if I take a projection onto the 0L and a projection onto the 1L, and I sum it up like this, I make a convex, I just make a sum like this, that essentially defines the projection of the code space, because any psi will then be written as some alpha 0L plus beta 1L after the action of this projection on the code space. So this is the code space which is sitting inside, and it takes any state psi which is outside the code space into the code space. It projects it based on where it is. A different phi which is located here will get projected to a different state inside the code space under the action of this projection operator. So that is the role of the projection operator, and it is a single operator which defines the code space for us. Another way of thinking about it is the identity operator on the code space. Okay? So the projection operator is nothing but the identity operator on the code space. Why? Because if the state is already inside the code space, then it does nothing to the state, right? So if I have, so if there is a state, let me call it some psi tilde, which belongs to the code space, then such a state can already be written as A0L plus B1L. And so the action of this projector onto the code space on such a state is going to again give me the same state, right? It's going to leave it invariant. So this is like an identity operator on the code space. It's as if the identity, you acted on the psi tilde state by just the identity operator. So that's the projector on the code space. So this is the second element in any error correction scheme, right? The third element is where the detection and correction comes. And this error detection and correction can be combined together into what is called a recovery operation. And I will denote this as R. So what is this recovery operation? So if you look at what we did for the bit flip code, you have your 3 data qubits. So this could be some encoded state with error probably, right? So what do we do to this? The way we drew the circuit is to say that we are going to now do these C naughts, right? Have 2 ancilla qubits, and we are going to take this information out and do measurements of the ancilla. But if I were to look at it and then conditioned on that measurement outcome, we were going to do unitary operations on the encoded qubits, right? We're going to do the X operation, one of the 3 single qubit X gates, right? That was the procedure. But that procedure can simply be thought of from a very just mathematical or algebraic point of view. I don't need to invoke all these ancilla qubits and syndrome measurements. What I can say is I do some measurement here, and conditioned on that, I perform some unitary. Right? And that unitary in the case of the bit flip code is simply either x1, x2 or x3. And the measurement is simply a projective measurement, as we saw, because your code words get mapped to, rather your code space gets mapped to one of 3 orthogonal subspaces. So it's simply a measurement, some kind of projective measurement, and I think I called this P1, P2, P3, right? And depending on whether if it was P1, you will do the unitary you will do is x1. If it was P2, the unitary you will do is x2, etc. So there is a measurement followed by unitary, right? And together, I will box this and call this a recovery operation, R, which is a CPTP map. Because as we already saw in the first few weeks of this course, unitary operations are nothing but a special case of CPTP maps, and measurement is also a special case of a CPTP map, right? There are 2 examples which we've already seen which fit under this umbrella of general quantum operations, right? So I can abstract out this whole process of error detection and error correction just for mathematical purposes as a single completely positive trace preserving map, and I will just call this the recovery map or the recovery operation. Okay, so a QEC scheme or protocol is characterized by these 3 objects. So when you say you have an error correcting scheme, you specify the noise. Sorry, I'm using N for the noise. You specify the code space via the projector on the code space, because the projector captures this completely, and then the recovery. So this set of 3 is what characterizes any quantum error correction scheme. So now what is the question we are trying to address here in writing down conditions for this? What we're trying to ask is, given a particular code, what is the set of error operators that can be corrected by the code? or given a particular noise channel, how do we characterize a code which can correct for errors due to that noise, right? And so this can be stated in the form of the theorem. So this is, state the theorem. These are called Knill-Laflamme conditions. So let's see be a quantum code. Note that when I state this theorem, there will be no reference to whether these are qubits, how many qubits are you going to encode this into, etc. Right? It's a general statement, and then you can now analyze all the known error correcting codes using this, and then you can try to see how to then generalize this and construct new or better error correcting codes. For example, is 9 the smallest number of qubits you need for a general to correct arbitrary single qubit errors? Turns out the answer is no, right? And you can get to that answer only if you understand these conditions for error correction. So let's see be a code and with a projector P, right? And consider some set of errors associated with some noise channel N. Okay. So there exists a recovery operation R such that after the action of the noise and the recovery on any state, I'm just writing a density matrix in general, right? We get back a density matrix that is up to some weight, so it's proportional to itself, right? For all rho which are such that they are for all, so let me just say this, for all density operators on the code space. What's a formal way of saying density operators on the code space? Formal way of saying this is for all rho such that P rho P 0. So the action of the projection on the code space leaves the density operator invariant, right? So this is a statement about, I'm not saying a statement here, okay. So there exists a recovery operation which satisfies this property if and only if P EI dagger EJP is alpha IJP for some complex numbers alpha ij, right? Of course, I and j run from whatever is the number of error operators. So this is, I will put capital N here. So this set of error operators here may be the error operators corresponding to the complete channel, or it could be some subset of errors, which are the only errors which are corrected by that code. That depends. But so long as these error operators satisfy this algebraic condition, right, then we say that whatever, we're going to show that there will always exist a recovery operation such that after the action of the noise followed by the recovery on any state on the code space, you get back a state, you get back the same state up to some overall factor. Okay, is the statement of this theorem clear? Any questions? Okay, so let's try to understand these conditions before we go about proving this theorem. So let me first note one thing. So look at this alpha ij, right? So this is basically like an n cross n matrix of complex numbers, right? Because for every e, so I can, I can say I and j are both 1. That gives me alpha 1 1 corresponding to e1 dagger e1. Then I have alpha 1 2 etc. alpha 1 n. So this is some matrix of complex numbers, n cross n matrix like this, right? What is more, this matrix has a special property. What is that? So you look at this condition. How are these alpha ij's defined? They are defined like this, right? So what is on the left hand side is in some sense, is the overlap between two error operators. EI and EJ are two of the Krauss operators of this channel, right? So EI dagger EJ is like an overlap, except it is sandwiched on either side by a projector on the code space. So in effect, this is like the overlap of the error operators on the code space. So if you recall these cartoon pictures we drew when we were discussing the 3-qubit code, we saw that the condition for error detection was that if I had different errors, E1, E2, etc., one could be X error on the first qubit, the other could be X error on the second qubit, etc. Then these different error operators had to map your code space to non-overlapping subspaces. This, what is on the left, is exactly that. It is capturing this overlap between two error operators when you restrict your attention to the code space. That's what these two projectors on either side are doing. They're saying you simply focus on the code space. I don't care about what's happening to some state here under E1. It may go somewhere. I don't care. I care about what happens to states inside the code space. So look at the overlap between two error operators, restricting your attention to the code space. So that's what's on the left hand side. And what the right hand side is telling us is this overlap should actually be a constant. This overlap, normally what is this? This is a matrix, right? This is an operator on the left hand side. But what's on the right hand side is basically a number, a complex number times identity on the code space, right? So the condition is effectively saying that this overlap must be given, must somehow be proportional to the code space itself, with some complex coefficient being that proportionality constant. And these complex coefficients have a special property, namely, this is alpha ij, right? It comes from the overlap of ei dagger ej. So now if I look at pej dagger eip, that is alpha ji. But this is nothing but alpha ij star, because I get this by taking the adjoint of this entire equation. So alpha ij represents, so this set represents, yes, what kind of a matrix is it? Are you guys still around? What kind of a matrix is alpha ij?
Hermitian matrix.
Yeah, indeed. It is an n cross n Hermitian matrix. Right? So just from the way the condition is written down, it becomes an n cross n Hermitian matrix. And this will be crucial in what we are going to say next. So let us first prove the sufficiency part. So let's go ahead and prove the statement. So the claim is that if such a condition is satisfied, then this set of errors for which this condition is satisfied is correctable by that code space, which is another way of saying that there exists a recovery operation which is going to bring back every state in the code space to something proportional to itself. That's what this part is saying, that it brings back every state in the code space to something proportional to itself. So that's what we have to show. So let us start by showing this, the easier part, which is the sufficiency part, right? So let's prove this first. So for sufficiency, we have to start from the condition and construct or show that there exists such a recovery operator, right? So how do we do that? Let's start from this condition. We've already noted that the alpha is Hermitian. Now, since alpha is Hermitian, so I'm just going to call this matrix itself as alpha. What happens? It is diagonalizable. So what does that mean? There exists a unitary operator which is going to convert it into diagonal form, right? Because it is Hermitian. So let's write down that unitary and that diagonal form. So there exists a U such that, so this is unitary, such that U dagger alpha U is a diagonal matrix D. Now take this unitary matrix. So this exists, right? Given this alpha, given this condition, right? This unitary exists. So now let Uij be the elements of this unitary. Now go back to this result which we showed earlier when we were discussing Krauss operators and the Krauss operator sum representation. If you recall, we showed that this Krauss decomposition of a channel is not unique. You can modify this Krauss decomposition provided you combine these Krauss operators with appropriate unitary coefficients, right? If I take linear combinations of these Krauss operators with unitary coefficients, then what I get is another Krauss representation for the same noise channel. So we're going to use this unitary to do that, right? So now we use the unitary freedom in Krauss representation to define a set of operators Fk such that Fk comes by combining these EIs, the so-called original error operators of the channel, using these unitaries, using the elements of this unitary matrix, right? So this was done in one of the earlier lectures. If you don't recall, please go back and look up that lecture where we showed that you can represent the same quantum channel via multiple Krauss representations, right? So using this unitary freedom in Krauss representation, we can define another set of Krauss operators for the same channel. So this Fk is also a Krauss representation for the same noise channel N. Now let us look at what happens to the QEC condition in the Fk representation. Remember, we started by saying that, so sufficiency means what? We assume that this condition holds, right? So we start from here, and then because alpha is Hermitian, we can diagonalize it. And in diagonalizing it, you get this unitary operator U, then you use that unitary operator in order to rewrite your Krauss operators into a different set. And what happens to this condition for this different set? So now if I write Fk dagger FLP, what does this look like in terms of the EI and EJ? So I can write this as sum over I and J, UIK, U, wait, what did I say? UIK EI is what I've written. Okay, so this becomes UJL star. Oh, it's FK dagger, sorry. So this is UIK star. And then I should have a UJL. Then P EI dagger EJP, right? So this is nothing but sum over ij. Remember, this is alpha ij. So this is uik star alpha ij ujl p, right? So this just comes from the QEC condition. And now what I have here is nothing but u dagger alpha u, the ijth element of that, times the projection onto the code space. But this is nothing but the diagonal operator d, ijth element of that. So that is nothing but dii. Sorry, this is the klth element. Yeah, I'm sorry. I summed over I and j. So this is kl. So this is dkk delta kl. So this is what the conditions look like in this modified Krauss representation. Why is this important? Because what this says is two things. It means that when k is equal to L, this is simply some number times P. When k is not equal to L, this right-hand side vanishes. Okay, so let me back up a little bit and repeat this argument again. So you know that these alphas are diagonalizable, right? So you start with this condition. The alpha ij's form the coefficients of a Hermitian matrix. Hermitian matrices are diagonalizable. And because they're diagonalizable, there exists a unitary operator, U, such that will cast it into this diagonal form. Now I use the elements of that unitary operator to modify the Krauss representation. And in this modified Krauss representation, the conditions take a diagonal form. Okay, so this is what I will call diagonal form of the QEC conditions. Any questions so far?
How do you reach to the box? I mean, capital D K L P, how it is written to small d K K L K L.
You're asking me about these last two steps?
Yes, last two steps.
Okay. So this comes from the fact that, so I'm summing over I and j. So this is alpha ij. This is elements of u dagger. This is elements of u, right? So this whole thing summed over I and j is nothing but this, right? This matrix multiplication, u dagger alpha u, the klth element of that. Is that step clear?
Yes, sir.
Okay. So then dagger alpha u is diagonal. It's a diagonal matrix D. And D
Okay.
basically has entries like this. So I'm defining D to have entries little d, D11, D22, etc., DNN. Okay. So that's what I call as D sub KK or whatever, right? So these are the elements of this diagonal matrix. And it's an n cross n diagonal matrix. Okay. Any other questions? Okay, so now let's look at this diagonal form of the condition. So for the same Krauss operator, this is saying something interesting. And for two different Krauss operators, it's essentially saying that the right-hand side vanishes. So let's look at the second part. What the second part is saying is precisely what I've been showing in these figures, that I take the code space and I act some error operator, FL, right? FL on P is what? So FL, so I break this into two parts, right? So the FLP is basically the action of one error operator, which is labeled L, on the code space. So this is P for me, right? The code space is being characterized by that projection operator P. So this is taking me to some subspace, right? Because now I'm talking about a projector. So it's taking me to some region of the larger Hilbert space. And Fk is taking me to a different region of the larger Hilbert space, such that, oops, if I look at the overlap function between Fk and Fl, there are no states in the overlap. So there is no overlap between these two subspaces, between these two parts onto which two different error operators are mapping the code space. So this is indicative of mutually orthogonal or non-overlapping subspaces. So Fk and Fl are mapping the code space to non-overlapping subspaces. That is what this condition is saying. When k is not equal to L for any two different error operators do not have any overlapping support, right, when they act on the code space. Now, what about the action of the same error operator on the code space? What is this overlap telling us? This is actually telling us how we can do the recovery fully. Okay, because not only do you need this fact that different code spaces should map you to non-overlapping parts, you also somehow want that the action of each error operator on the code space be reversible in some way. So there are two parts to it, if you recall. There is a measurement and there is a unitary, right? Finally, the action of the error on the code space should be reversible by the action of a unitary. Only then did we say that these are correctable errors, right? Because otherwise, we don't have a way of reversing these operations, right? So we are breaking down these error operators into a set where the action of two different error operators is non-overlapping. So this implies that there is a measurement, or that it is possible to do error detection, right? That is guaranteed by this. The unitary property is what is guaranteed by this. How is that? Well, for that, we need to use another trick from linear algebra, which is called polar decomposition. So the polar decomposition, so I will refer you to one of the early chapters of Nielsen and Chuang for this. So this is section 2110 of Nielsen and Chuang. This is one of the standard decompositions in linear algebra. So those of you who already have done a course in linear algebra may know of this. Does anybody know what polar decomposition is here? Or anybody recall what it is? Okay, so it basically says that if I have a linear operator A, can be decomposed as the product of a unitary operator and a positive operator. Where this positive operator is actually nothing but square root A dagger A. Remember, for any linear operator, A dagger A is positive, and you're taking the positive square root of that operator. So every linear operator can be decomposed as a unitary times the square root of a dagger a. So this is what the polar decomposition is. I'm not going to go into the proof, etc. I will refer you simply to this section in Nielsen Schwang where it is stated and proved and all of that. In fact, one way to prove singular value decomposition is using the polar decomposition of the operator, right? So many people also relate this to the singular value decomposition like that. Okay, so using this fact that any operator can be decomposed as a unitary times a positive operator, let us now try to decompose these error operators via the polar decomposition. Okay, so what happens if we do a polar decomposition of these error operators? And I'm going to do a polar decomposition not of just the error operator itself, because I don't so much care about the error operators, whether the error operator itself is unitary or not, right? That will be a bonus. And that's what happens in the case of, say, the Pauli kind of noise channels, right? Like what we had, the bit flip or the phase flip, etc. But what I'm more interested in is the error operator times the projection on the code space. So this product object is what I'm interested in. And I want to see if this is really like a unitary or not, right? And the claim is somehow this condition guarantees that this is like a unitary operator. The action of the error on the code space is like a unitary operator. So what does this like mean? See, so you do a polar decomposition of this. So what does it say? It says that there is a unitary operator UK, right? The K subscript for each error operator FK times square root of P FK dagger FKP. And now you see where the error correction condition comes in. So this is now nothing but square root of these diagonal entries, right, that you got by diagonalizing the alpha matrix times P. And this comes from the diagonal form of the QEC condition. Right? So now you realize that the action of every error operator is indeed a unitary of the form UK up to this number. So it's essentially a scaled unitary operator. So each error operator which satisfies the condition, right, is a scaled unitary transformation on the code space. So this is important. I keep repeating, we are not interested in what these error operators do to the rest of the Hilbert space. We are only interested in what they do to the code space. So it's always accompanied by this projection on the code space. All this algebraic analysis is always with reference to the code space. So the diagonal form of the QEC condition, I've separated it into two parts. One tells me what happens when K is not equal to L. The other part tells me what happens when for the same error operator, right? And for the same error operator, the polar decomposition tells us that the error operator is nothing but a scaled unitary on the code space. And this then guarantees the reversibility, right? So this implies reversibility again as far as the code space is concerned. So this part of the error correction condition guarantees that I have found the right subspace, right, such that I can now reverse the action of the error operators on states within this subspace, right? So now we can construct, so putting together both these parts, the fact that FK dagger FL has no support, right, that this overlap gives me 0, and the fact that FK dagger FK is essentially a constant times the projection on the code space. Putting these two things together, I can construct so-called recovery operators. So I will call these R sub k. So for every error, I now have associated with it a particular unitary UK. So I simply have to take the adjoint of that unitary operator. I have to take care of the scaling, which is this DKK part here, right? So I'm going to claim that these recovery operators are simply of the form P UK dagger. So if you remember, what acts on the states first is this UK dagger. This reverses the unitary, and the P simply projects back to the code space. So why is the recovery operator of this form? Let's again break this down. So if you recall, you need error detection and then correction. So the error detection needs orthogonal projectors, right? So what are these orthogonal projectors? If you remember, we had constructed these different subspaces, right? So if I go back to the 3-qubit bit flip code, then I had constructed projectors like this based on where the error occurred. So if the error occurred on the 3rd qubit, then this is the projector associated with that subspace onto which the error maps the code space, right? Similarly, I had 0, 1, 0, 0, 1, 0, and then so error detection needs a set of orthogonal projectors. So for example, this is the case of the 3-qubit bit flip. So how do I get these recovery operators? I get these as a combination of, first I do this projective measurement to decide which subspace the state is in. And then once I know that it is in this subspace, I know that I have to do an X3 operation. Once I know that it is in this subspace, I do an X2 operation. So this is the unitary part. So there are orthogonal projectors and then there are unitaries which do the error correction itself, right? But first I need to identify these orthogonal projections for error detection. And how do I do that in this abstract setting using these? Now all that I know is that every error operator is of this form UKP. But look at these unitaries more closely. So these orthogonal projectors PK actually come from these unitaries itself, right? Where these unitaries are coming from doing a polar decomposition of the error operators. So these PKs are orthogonal projectors. First of all, we have to argue that, well, really, how? Well, we have to argue that they are first projectors. So let's do PK squared. So that is UKP, UK dagger, UKP, UK dagger. Yes, so this is identity. P squared is P. P is the projector on the code space. So this gets me back PK, right? So this tells me that they are projection operators. And then I'm going to say that they're orthogonal projectors. Well, they're orthogonal because the FKs don't have an overlap with the FLs. So when K and L are distinct, the error operators don't have an overlap. So the corresponding unitaries should not have an overlap, right? So the associated projectors should not have an overlap. So if I do PKPL, that is UKP, UK dagger, ULP, UL dagger. And this is nothing but FK dagger FL divided by some numbers. That doesn't matter. Which actually vanishes for all k not equal to n. So the product of these two projectors vanishes whenever k is not equal to L, because again going back to the error correction condition, this overlap vanishes whenever k is not equal to L. So because of these two reasons, I have a set of projectors which are simply defined by the action of this unitary on the code space projector. So if you go back to the 3-qubit code again, that is where these projectors actually came from. So this is the code space, remember. And then what error was this? This is the X3 error. So this is actually, if you think about it, X3, P, X3. This is X2, P, X2. This is X1, P, X1. So each error, which in this case is simply a unitary operator, acting on the code space projector, maps me to an orthogonal projector, right? So that is what gives me the fact that I have orthogonal projectors that come out of this error correction condition. So that is the first part, the error detection part. So these are the, so let me just say define these PKs. So this is the error detection part. So the full error correction part now requires us to apply the corresponding unitary UK. After, if you get the measurement outcome PK, you will have to apply the unitary UK, right? So this simply becomes, sorry, you have to apply UK dagger, right? So this is the reversal of UK, and this detects the error FK associated with UK. So I hope this makes it clear. So then I have UK dagger, UKP, UK dagger, and this is nothing but P, UK dagger. So this is what I called the recovery operators, RK here. So that is where I got this form of the recovery operator from. Okay. So once I do the polar decomposition, I get unitaries UK, and then the recovery is simply UK dagger followed by projection on the code space. You can break it down as a product of an orthogonal projection times the inverse of the unitary operator, but the math will tell you that this is nothing but this itself, which is PUK dagger. So yeah. Okay, so that's it. I have identified a recovery operator. So I now need, the last step is to show that, so putting it all together, I have a recovery map R, which has Krauss operators RK, which are nothing but PUK dagger, and these actually came from doing this sequence. First a projection, then the unitary reversal. So this is the same thing actually, right? And now I need to show that if I do this combination of noise followed by this particular recovery operator, I should get back the original state. So do I get it back? So let's do the last check. So this is sum over K and L. So first of all, there are, so I'm going to use the FK representation, right? So there is FK row, FK dagger, then RL of this, RL dagger, right? Two maps, right? There's a composite. So this is the composition. So first the noise, then the recovery. Recovery has Krauss operators RL. Noise has Krauss operators FK. Now use the fact that the RL is nothing but P UL dagger and FK is nothing but UK P. Remember, rho is nothing but P rho P dagger, P rho P, right? Because this is all, for all rho within the code space, right? Rho is such that it is inside the code space, right? So then this gives me again UK dagger ULP, except it has to be accompanied by these factors now, which is basically just DKK actually. So this whole thing has to be multiplied by this number. And now what happens? Whenever k is not equal to L, this sum vanishes. So this becomes a sum over a single index. But UK dagger UK is nothing but P, right? Sorry, UK dagger UK is nothing but identity. So this just gives me P. So it just gives me P rho P with a sum over K DKK, which is a sum over all these diagonal entries, right? Because each of these gives me a delta, right? Because these unitaries are also orthogonal since the FKs are orthogonal. That's what we saw earlier, right? So this product vanishes whenever K is not equal to L. So what I end up with is therefore a state that is proportional to the initial state in the code space. So long as, so note that I had to crucially use this fact that P rho P is rho. So for all states in the code space, I recover the state up to some constant or up to some scaling, right? So that we have shown this error correction property that was claimed. The one final thing which I need to show is that this recovery map that I wrote down, I claim that it is a CPTP map at the beginning, right? So is it a CPTP map? I've written down some set of Krauss operators. So that takes care of the CP property. Is this a trace preserving map? So let us check that condition once. So it turns out, so let's do this. So RK dagger RK, right? That's what we need to check. So let's rewrite this in terms of RK dagger becomes UK P UK dagger UK P UK dagger. Sorry. So this is UK P times P UK dagger. So this becomes. So what are these? These are a sum of orthogonal projectors. We already saw that, right? And whenever I have a sum of orthogonal projections on some larger space of this space, then such a sum cannot exceed identity on that space, right? Because what are these projections? They are projections onto this, I'm just drawing it bigger, it's the same space. They're projections onto this larger encoded space, right? So they are projections onto these different parts of this encoded space, P2, etc., PK. So the sum of these projections should cover the entire space, or it should be smaller than the entire space. So it cannot be larger than identity on that space. So either it's a complete covering of that space, or it's an incomplete covering, which means it's identity minus something. So whatever it is, this has to be less than identity on its range, right? So this is what we need to guarantee that the map is trace preserving. So what we have shown actually is that this map is trace non-increasing. In the case of some codes like the 3-qubit code, it's a perfect partitioning of the 3-qubit space, right? The 3-qubit bit flip code or the 3-qubit phase flip code, it was a perfect partitioning of the encoded space. In some other cases, like the Shor code, it will not be a perfect partitioning of the encoded space. There will be some leftover space in this encoded Hilbert space. In which case, the map will be trace non-increasing. And as we've seen earlier, trace non-increasing can always be made trace preserving by adding an additional operator, right? So it can always be made trace preserving. Okay, so this completes one part of this proof, which is a sufficiency part, but this is the part which really tells us what these conditions really mean and how they allow us to construct a recovery operator. So I will stop here today and we'll do the necessary part in the next class. Questions?
Ma'am, yes. So in error, like, can you explain the error detection part? Like, where exactly does the UK comes into picture?
Yeah, so I can, maybe it's better done with a figure. So I have this code space and I have the encoded space. The code space, I mean, by encoded space, I simply mean, so let's say, for example, we went from C2 to C2 tensor n, right? Some n qubit, some larger space, right? And now I have these different error operators. I'm now working in this F basis where I have rotated, basically I've changed to a different set of Krauss operators such that they satisfy this condition that Fk dagger FLP is some constant times delta KLP, right? So now this takes the F1 takes the code space to some part of this larger space, right? When I say takes the code space, it means it takes states inside the code space to some part in this larger space. Where it takes me to is associated with a projector, right? And that projector comes from the action of a unitary on the code space. And that unitary comes from, so that unitary, how is that associated with F1? Well, it comes from a polar decomposition of F1. So this now gives me D11 U1P. That is what the error correction conditions guarantee. So the action of the error F1 on the code space is like the action of a unitary U1 on the code space up to some weight D11. And because when I add the projector on either side with a unitary, when I take any projection operator and I conjugate it with a unitary like this, you can see that what I get again is a projector because it squares to itself, right? So the action of this error operator on the code space projector gives me another projector because the action of the code space is like a unitary on, because the action of this error is like a unitary on the code space. Similarly for F2, F2P is proportional to U2P, where U2 is a unitary, and that gives me a projector P2, where P2 is U2P, U2 dagger. Does this answer your question, Sriram?
Yes, ma'am. Yes. So here, like F1 is the error that takes it from the initial code space that is P
Yeah.
to a code space that is P1.
To a different space, not the code space anymore, right? The code space
Right.
is still
Yes. 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 Right.
P.
Yes.
Mm.
Okay. Okay. Got it. Got it. Okay.
What the error correction conditions guarantee is, first of all, that F1 is proportional to a unitary U1 on P. And secondly, these different projectors P1 and P2 are orthogonal. They do not have any overlap because of this. Well, because of this delta KL that's sitting here. So when I have F1 dagger F2, that becomes like U1P, U1 dagger, U2P, U2 dagger. But that's like P1, P2, and that becomes 0 since 1 is not equal to 2. So whenever K is not equal to L, there's a delta KL sitting here. That guarantees that these associated projections are orthogonal, and therefore I have unambiguous error detection and hence correction. Okay.
Yes, ma'am. And what is the significance of that F, K, and FL being the same?
That's where I got the unitarity part, no? When K and L are the same, then this is F1 dagger, F1P is D11P. So when I do a polar decomposition of this,
Right.
this is the term that sits inside the square root of the polar decomposition.
Right. Yes.
And that becomes a number simply because of this error correction condition.
Right.
Yeah, this part. Yeah.
Yes, ma'am. Yes. Okay. Got it.
Okay. Any other questions? Okay, so I will not be teaching tomorrow. Instead, you'll have the tutorial on Saturday. Okay, so we won't have a lecture tomorrow. So we'll continue with the proof of this on next Monday's lecture, the proof of the converse part, which is the necessary part. Okay, so you guys will have the tutorial on Saturday. I already sent the mail. I've uploaded tutorial 2 also. So on Saturday will be the tutorial, and then we'll meet again next Monday. Okay. All right. See you then.